So we've used these terms a lot, rock, mineral, metal, and I just want to make sure that we understand the distinction between them. So a mineral is defined as a naturally occurring inorganic solid with a specific chemical composition and a specific internal crystal structure. So it is naturally occurring, it is inorganic, it's a solid crystalline structure with a specific chemical formula. And so I've provided 2 links to some really educational TikTok videos by Hank Green describing how water in the form of ice is technically a mineral. Yes, it is a mineral, which means since we are mostly composed of water, that might make us lava monsters. So just check out the videos. They're really cute and it makes you think a little bit. So moving on from that, metals like iron, copper, aluminum, or gold, these come from mineral ores. But once we purify them, we extract them from the earth and we purify them, the metals are no longer crystalline, and thus they're not considered minerals any longer, because again, you have to have a specific crystal structure in order to be considered a mineral. And then finally, a rock is simply a solid cohesive aggregate of one or more minerals. So in that case, ice, being composed only of water, is also considered a rock. It is a monomineralic rock. It is a rock made up of one mineral, but ice is a rock. The more you know. These rocks are formed through what we call the rock cycle, which is just a cycle that creates and recycles rocks on our surface. So these rocks are formed and destroyed by different parts of the rock cycle. There are 3 major rock classifications. We have igneous rocks. Those are solidified from hot, molten magma or lava. Most of the rocks on our surface are igneous rocks. And that's because magma extruded to the surface from volcanic vents cools really quickly and making those finely crystalline rocks like basalt or andesite or granite that we use on our countertops. So those are the igneous rocks. Next, we have metamorphic rocks, and metamorphic rocks could either be metamorphosed rocks that were sedimentary to begin with, they could have been igneous to begin with, or they could have been other metamorphic rocks. But these rocks form from the melting, contorting, and recrystallization of other rocks. This happens largely deep within the earth, where it's really, really hot and full of pressure. And that combination of temperature, high temperatures and high pressure are going to squeeze and fold, heat, and transform solid rock into other forms of rock. Basically, it changes what it looks like and also the chemical composition of those rocks. And so examples of this include diamonds, jade, graphite, marble, quartzite, and slate. Each of those rocks, yes, diamond being a rock, each of those rocks have a different starting rock that they come from. So for example, marble, which you probably know what it looks like. Marble is just metamorphosed limestone. So the gray dull rock that you see around East Tennessee, all of that is limestone. You metamorphose that limestone and it turns into beautiful marble. And then finally, we have sedimentary rocks. Sedimentary rocks are formed when loose grains of other rocks, could have been metamorphic rocks or igneous rocks, are solidified, cemented together, and form a new rock. And this usually takes a lot of time, but it could also require some pressure as well. Some examples of sedimentary rock include sandstone, which we also have here in East Tennessee, mudstone, limestone, and then a special type of sedimentary rock called a chemically precipitated sedimentary rock is salts. Most notably halite, which is table salt, sodium chloride. And so halite is probably one of the very few rocks that we actually eat on a normal basis. Here we have the depiction of the rock cycle. It includes a variety of geological processes that can transform any rock, even rocks of the same type. So here we have depicted on this dashed line Earth's surface. So on Earth's surface, we have a whole bunch of sedimentary rocks. Those sedimentary rocks can also turn into other sedimentary rocks at some point. Those sedimentary rocks can also be subjected to melting and recrystallization through processes like subduction, for example, that allow them to turn into igneous rocks once they come to the surface. You can also have igneous rocks come from pieces of metamorphic rocks that are subjected to melting and crystallization. Igneous rocks can also be metamorphosed on their own, turning them into metamorphic rock. And then pieces of metamorphic rock that fall away from the main bedrock or core stone can turn into sedimentary rocks if they eventually get solidified and consolidated together. So once these rocks are at the surface, they're subjected to a lot of things that aren't conducive to them staying around a long while, including acid rain and oxygen. The thing about water coming from the sky is that it's already naturally acidic. And so even if we, removed all of the CO2 that we've pumped into the atmosphere from the burning of fossil fuels, our water would still, or our rain would still be considered acid rain. And so once these rocks are exposed to the atmosphere and that acid rain, it begins a process called weathering. And weathering is the breakdown of rocks through contact with Earth's atmosphere, water, or biological organisms. So there are organisms that, such like plants and their roots, that excrete acidic enzymes that will help the weathering process to break down these rocks. So the deposition of these materials is called sedimentation. And when we remove and transport those rock pieces that have been weathered out to another place, we call that erosion. So the confluence of weathering, sedimentation, and erosion can further carve out these rocks. We see here beautiful outcrop of soft sedimentary rocks that were deposited during the Tertiary period about 63 to 40 million years ago. This is what we have at the Pink Cliffs of Bryce Canyon National Park in the United States. And because this rock was soft and subjected to weathering after being exposed to the atmosphere, it allowed these flutes and spires to be generated. And those are also called hoodoos. And all of this is just the product of weathering and erosion. So those are natural processes. And I'm now going to introduce to you the economic side of geology in economic geology and mineralogy. The Earth, our planet, is very, very rich in different mineral species. There's this number is outdated, I think there's over 5,200 different mineral species on our planet. My boss, when I was a postdoc in my last job, he's one of the world's foremost mineralogists on Earth. And his whole thing is understanding when on Earth's history did we get different minerals. And he's got this fantastic talk that says basically once we had life evolve on Earth, that opened the door for a whole bunch of new mineral species to come about. So exciting. But economic mineralogy is the study of resources that are valuable for manufacturing and trade. In other words, those minerals that are of value and hold some economic value as items for trade or for sale. And so most economic minerals are metal ores, of course, because they're extremely important in infrastructure and construction. The mining, processing, and distribution of these materials has broad implications for both our culture and our environment. For our culture, placing value on rocks of different types, minerals of different types, and for our environment, the entire process of extracting these natural resources for the distribution and trade. Here we have some statistics on the world industrial consumption of different metals. So the metals that are consumed in the greatest quantity by the world include iron, aluminum, manganese, copper, and chromium and nickel. And so Russia, China, Canada, the United States, and Australia, for example, are especially rich in their natural mineral sources. South Africa, because of the geological type of rocks that they have there, is unusually rich in diamonds, gold, and other valuable minerals. And as the developed world has taken advantage of that fact for decades, often exploiting these communities and these ecosystems. In 2011, geologists announced the discovery of an estimated $1 trillion worth of metals and other valuable minerals in Afghanistan. And so critics claimed that this announcement was merely an excuse for continued military occupation of the troubled country of Afghanistan. But in any case, difficult terrain and political instability will make these deposits that are economically favorable really difficult to access. And so the rapid growth of green technologies like renewable energy and electronic vehicles has made a group of rare earth metals especially important. So we could be seeing shifts in what is deemed as economically valuable. For example, transitioning from coal energy to renewable resources like solar requires an entirely different suite of minerals and metals to be extracted from the earth. There are also non-metal resources that are important, including gravel, clay, glass, as well as salts. So we have sand and gravel that is used mostly for building and road construction. This is by far the greatest volume and dollar value of all non-metal resources that we use, that's sand and gravel. There's also high purity silica sand, which is what we use to make glass. So the glass in your window panes is actually made up of quartz. It's made up of silica, which is sand, and they process it and treat it such that it is usable for glass. Limestone, which we have a whole lot of here in our part of the country, is mined and quarried for concrete, and it's also crushed for road rock. Halite, or rock salt, sodium chloride, is used for water softening and ice melting on winter roads in northern areas of the United States, or it could be refined and we could use it as table salt, as we do. And that, along with gypsum, which is a similar type of mineral to halite in that it is chemically precipitated. It is the product of evaporation. Gypsum is used in plaster wallboard. And so these materials are retrieved from surface pit mines and quarries where they can be deposited by glaciers or winds or even ancient oceans. The Earth right now provides almost all of our fuel that we use. Currently, society functions largely on energy that's produced from geological deposits of oil, coal, and natural gas. These being carbon-based. This is also carbon-based, but natural gas is primarily in the form of methane, CH4. These fuels collectively are created over millions of years as extreme heat and pressure transformed the remains of ancient organisms. Again, largely plants that were not degraded at the Earth's surface at the time that they died. Instead, they got buried and transformed into these natural products here. So although they are organic rather than mineral materials, they can be considered part of economic mineralogy and are important geological resources. These, of course, are non-renewable sources of energy in any realistic time frame, meaning, sure, if we buried a whole bunch of plants now and waited 300 million years, we could produce some more natural gas, coal, and oil. But again, that is not a realistic time frame for human purposes, where we only live, maybe if we're lucky, like 80 years or so. So nuclear energy is an alternative. This runs on uranium, which is a radioactive mineral. And this nuclear energy provides about 20% of our electricity, including here in the Tennessee River Valley. We also use some nuclear energy that is generated by plants at TVA. So extracting and purifying these resources, of course, can have severe environmental and social consequences. In addition to the extraction process, it actually uses a whole bunch of water to extract these materials. And that water is used in washing the crushed ore with cyanide and other solutions, for example. So the USGS, the US Geological Survey, in Nevada, they estimate that in that arid part of the country, mining consumes about 60 million gallons of water per day. And that's not even the water that's included in the purification process and the processing to make the sellable product. Mining and drilling degrade water quality, as we just discussed. There are many techniques for extracting these geological materials. As we saw at the top of this lecture, there's strip mining, that mountaintop removal mining. There's also open pit mining and underground mining. There's something else called placer mining, where water cannons are used to erode hillsides and nuggets of the materials that are economically important are washed from the stream sediments. This method unfortunately chokes stream ecosystems with sediment and making them extremely unhealthy. There's also underground mining, where water seeps into the mine shafts and can dissolve toxic minerals and then seep into groundwater or other streams and lakes. So instead of those toxic minerals being safely buried away for a great number of years, we are pounding them with water that will then make those toxic minerals be exposed and able to seep into our groundwater and our streams and our lakes. Another thing that we have just touched on briefly is this thing called hydraulic fracturing. And this is used to extract methane gas, so that natural gas from coal deposits that are too deep or too dispersed for mining. This is really, really bad on water supplies. And it uses a mixture of water, sand, and toxic chemicals to pump out higher yields of this natural gas. So each well produces up to 75,000 liters of salty water per day. And then dumping this toxic waste into streams causes widespread pollution. And this is all just to boost the output of a single well here to release more and more gas. So not only is it using a whole bunch of water, but it's also spewing lots of chemicals out into the environment that are extremely hard to clean up. So this often disrupts aquifers and it contaminates wells as well. There is a video for you to watch on hydraulic fracturing on the YouTube, so please watch that. We also have surface mining that just devastates entire landscapes. Here we have a surface mine. As you can see, it's just taken up a massive amount of the terrain here in this landscape. And this is an open pit mine. It's used to extract massive beds of metal ores or other minerals. Here we have one that is in Salt Lake City, Utah, that is about 2,600 feet deep and nearly 2.5 miles wide. They were able to extract from this open pit mine about 5 billion tons of copper ore, but they've also, of course, in doing that, left this open pit that has not seen any restoration efforts at all. So a chief environmental challenge of mining of this type, this open pit mining, is that groundwater begins to accumulate in the pit. So in metal mines, a toxic soup results. So imagine here just a lake full of toxic materials. So no one yet knows how to detoxify these lakes. And of course, those lakes pose a danger to natural wildlife as well as nearby watersheds. Moving now to processing contaminants in the air, water, and soil as a process after these extraction methods have been employed. So metals are extracted from ores by heating or by using chemical solvents in the bedrock. Both processes, both heating and using chemical solvents, releases large quantities of toxic materials that can be even more environmentally hazardous than the mining itself. So smelting is a process of basically roasting the rock material to release the metals from the ore. So the smelting is a major source of air pollution. And we also see this in Ducktown, Tennessee, where sulfur dioxide poisoned about 50 square miles. So in this area, in Ducktown, Tennessee, where smelting was taking place, there were dense clouds of sulfur dioxide released from the sulfide ores that were being smelted, and that poisoned the vegetation, and it also acidified the soil. And so when rains came down and washed the soil off the denuded land, this created a barren moonscape. Basically, nothing could grow there, sort of just like the moon. So recently, upward of $250,000 per year has been spent on cleaning up this effort. But if you were to go to visit Ducktown, Tennessee, you would see that the trees are really spindly and feeble, and it's not an adequate cleanup effort. In addition to measures using heat, like smelting, we also have chemical extraction. And chemical extraction is used to dissolve or mobilize pulverized ore, but it uses and pollutes a great deal of water. A widely used method is called heap leach extraction, which involves piling crushed ore in huge heaps and then spraying it with a dilute alkaline cyanide solution. So this method is really, really good at dissolving gold from ore of interest, but as you can imagine, it's spraying a whole bunch of cyanide into the environment.
In the Smoky Mountains of eastern Tennessee, there's a federal Superfund site twice the size of Manhattan, where copper mines and sulfuric acid plants had turned the Copper Basin into an environmental disaster zone.
Used to, when I was a kid, we'd have to drive 30 miles to see a deer.
But not now, after more than $70 million of restoration work.
We have a tremendous amount of turkey. We have deer, see deer regularly. I saw 2 right out there just the other day. A lot of snakes, squirrels. We've had bear spotted, beaver, groundhog.
Acid rain caused by roasting ore to burn off sulfur eventually denuded the landscape for 50 square miles. Occidental Petroleum inherited the problem and in 2001 began to restore 12 miles of streams and to clean the water from abandoned mines. Federal and state authorities are monitoring their progress. Until recently, streams running through the old mines were picking up thousands of pounds of metal and dumping it into the Ocoee River every day. The water was so acidic, it could dissolve steel. This plant treats 430,000 gallons of water a minute. Creek water is pumped into a mixing tank and bubbled with air. Lime slurry is added to precipitate the metals. The solids settle to the bottom of an old mine pit, and clean water is then discharged back into the creek.
At this time, we were catching 90% of all the acid and metals that was once entering the Ocoee River.
With the mines now closed, the Ocoee provides jobs and recreation for the region. Keeping it clean is the top priority.
And it's going to run down through a pipe.
Miles of pipe have been laid to route good water around some of the old mines. 300 acres of mine tailings have been converted into a lush meadow.
It's very much in pretty good condition and probably available for various land uses, post-mining land uses.
One last stretch of creek still needs work, but within a few years, the Copper Basin will become a recreation area with 32 miles of hiking and horse trails open to the public. For Assignment Earth, I'm Gary Stryker.
So it's wonderful to see that with some focused attention on specific problem sites, we can change the entire trajectory of these post-mine lands. What are some other things that we can do to make sure that our impact on the environment is not as great when we're extracting resources from the earth? Well, we can begin to recycle these materials, which saves energy as well as the materials themselves. Some waste products are already being exploited, especially for scarce or valuable metals. Aluminum, for instance, must be extracted from bauxite by electrolysis, which is very expensive and also energy intensive. So the high value of aluminum scrap, which is about 2,000 a ton versus 200 for iron, gives consumers plenty of incentive to deliver their cans for collection. Recycling waste aluminum, like your beverage cans, consumes about 1/20 of the energy of extracting new aluminum. And a fun fact is that about 75% of all aluminum ever mined is still being used today. So the take-home message here is that when you're choosing beverages from the gas station, for example, choose drinks that are in aluminum cans over plastic bottles, and then recycle those aluminum cans. Recycling is so rapid and effective that half of all the aluminum cans now on a grocer's shelf will be made into another can within 2 months. That's amazing. Nearly 2/3 of all aluminum beverages in the US are recycled, which is up from only 15% about 20 years ago. Other commonly recycled metals include gold, silver, copper, lead, iron, and steel. Platinum, for example, is the catalyst that's used in catalytic converters in car exhaust, and that's valuable enough to be regularly retrieved and recycled from used cars. So we have the infrastructure in place. We just need to make it more of a priority. So here are some benefits of recycling in terms of energy. We have on the left here the different products like glass, steel, and plastics. And then we have the energy requirement for generating new products or the energy required for generating products from scrap. And so by and large, you can see that the energy requirement in megajoules per kilogram is much, much lower for each of these products if we were to get them from scrap versus brand new. New materials can replace mined resources. Plastics aren't all bad. They lower our dependency on extracted precious metals, but of course this is at a cost. Of course, you need to extract the oil and petroleum in order to create the plastic in the first place, but it replaces our need for other things like iron and steel, which allows us to avoid mining those things. Mineral and metal consumption can be reduced by new materials or new technologies that are developed to replace traditional ones. So for an example here, the introduction of the plastic pipe has decreased our consumption of steel pipes, lead pipes, or copper pipes, which are actually pretty darn expensive. Another example here is the introduction of fiber optic technology and satellite communication, which reduces the need for copper telephone wires. You all probably don't even know what a landline phone looks like with a cord, but those required copper. And so now that we have fiber optic technology and satellite communication, we are no longer reliant upon those.